Let's talk about gravity, gravity part 3. I'm repeating myself again, just repeating the basic physics, but also I have to redo the whole part 3 because YouTube somehow managed to remove the whole audio from the other video that I actually made yesterday. I talked to them, but I sent a message via email. That's the only way you can reach them, and they have not answered yet. So anyway, who knows what's so dangerous about talking about gravity? Gravity part 3. What is gravity? Gravity is a force. No, I'm just kidding. Gravity is not a force. Okay, not a force of itself. Gravity is a term, a word, with which we describe the direction, the result of a force, of many forces at play. Many forces that come together create what we then call gravity, but gravity is just a result. It has a direction, and that direction is not just down, it can also go up. Can go to the sides. Okay? Gravity's direction is not just down, gravity's direction goes up as well, gravity's direction goes to the sides. That's gravity is the result of all of these influences at play coming together. Gravity is not a force of itself. So yes, gravity exists, but not as a force of itself. So when people say gravity doesn't exist, they are halfway true, okay, but also halfway wrong, because yes, gravity exists, but not as most people understand it, thanks to mind programming, thanks to images, animations, and everything that have all these things that has led them to believe that gravity is a force of itself, and part of that is the ball earth deception, because they argue that earth is a ball because of gravity, and there's an attraction going on within earth, from the middle of earth, that is drawing or attracting or pulling objects to earth. But that's a lie. That's not actually gravity. Gravity does exist, but not in this way. So gravity's direction goes up as well. Doesn't just go down, goes into all kinds of directions, because gravity is just a term with which we describe a result of forces. Many forces at play coming together, influencing each other, such as pressure of the medium, air pressure for example, and surface tension of an object, or of a material such as water. You have a water surface tension. All of these things are coming together, and it creates a result. That's what we're observing, and it can go up or down. Okay, the direction of that result, of that resulting force, can go up and down, can go to the sides. So that's gravity. Gravity is not a force of itself that comes out of the middle of something. Okay, so when people argue that gravity is Earth's attraction, then they're wrong. If they think, or if they believe that there's a force from the middle of Earth attracting material, because if there were a force of itself, then it would be much easier for that force to pull lightweight objects to itself. It wouldn't care about lightweight objects if it can hold whole oceans, masses, bodies of oceans, of water, close to itself. Yet, it's so easy for a bird to escape that force. It's so easy for a lightweight balloon to escape that. Of course, then something doesn't add up. The theory is wrong. So the correct theory is that gravity is not a force of itself, it's a sum of forces, a result. And that result has a direction. Many forces at play create a direction in which an object moves. If that object does not have a force of itself, such as, for example, water drops. They don't have an engine or something inside them that makes them move. Okay? It's not like people that have a spirit that is a force from within that makes people move, um, or a helicopter in the sky or an airplane has a force of itself, creating that force to move forward. Okay? Then that is not what I am talking about. I am talking about objects that don't have a force of itself, such as water drops, that can be spherical, somewhat spherical, in small quantities, small amounts of water. They are spherical, but not because there's a force within themselves. And why do they drop through the gas? Not because there is a force within themselves, but because of gravity, because of surrounding medium, surrounding conditions and surface tension. Okay, why is the drop spherical? Because of surface tension and the pressure of the air that surrounds the drop. So whenever drops become bigger, they become less spherical, because it puts so much force onto the surface tension of the water, and the area increases. The bigger that drop becomes, the area of the surface increases. So it starts to have all kinds of shapes, but not spherical. Okay, so when people argue that gravity creates spherical shapes, yes, when the material comes in small quantities, and Earth does not come in small quantity. Okay, we have the most quantity is Earth. Actually, Earth material is metal, is huge mass. As waters of oceans, everything that, okay, it's huge mass. And so that all that is being attracted, but a feather is just like floating through the air. Of course, it's somehow coming to Earth. Let's take a better example. Helium balloon is rising up. It's a lightweight, so it's completely escaping that force. Of course, that's a bunch of wish-wash. Gravity is not a force of itself. It comes out of the middle of the Earth. Earth does not have that kind of attraction to itself. Why things move up or down in space depends on their own properties, which is mass, for example, and the surrounding medium. And that creates again a result, a direction into which objects move. And if, for example, there is there is wind in the air, and you have a hot air balloon, for example, that just rises up through the air, but then there comes wind, is an outside force that pushes that air balloon, hot air balloon, into another direction, slightly maybe to the left, diagonally, up and left. You see? So that is gravity. So then now the result of forces points slightly diagonal, and that's still gravity. You see what I'm saying? So gravity is not just pointing straight down, gravity is not just pointing straight up. gravity is pointing into all kinds of directions because it describes the result of all the forces at play. Okay? So when people argue, oh, Earth is a ball because of gravity, that doesn't make sense at all. Okay? Because that would mean that some outward force is actually pressing everything together to shape Earth into a ball. And we know that air pressure is fairly weak actually. Water pressure is already much higher, right? But still air has some kind of pressure, of course. And another thing is polarity. For example, you have plus and minus. You can rub a balloon which is made of plastic or some kind of rubber. You can rub it on your shirt and then it sticks to the wall. You can put it onto the wall and it will stay there for a few minutes. So you could now argue the wall has an attraction and it is attracting the balloon. But why? Because of polarity. Okay? It's not because there is an original force within that wall that attracts things. You see what I'm saying? So, gravity is often misunderstood. Also, buoyancy is just part of gravity. Buoyancy is when, for example, ships float on water. That's buoyancy. And it's just floating there. It stays there. But gravity describes a direction. When, for example, water drops come from clouds down to Earth, that's gravity. When a helium balloon rises up through the air, then that's gravity. Once then the helium balloon rises up into the air and reaches its balance, reaches a point in altitude where it's completely, all the forces are being balanced out, then again it's buoyancy. And for example, a human body in water, because the human body contains of 60% of water, seems weightless because of buoyancy. That's why it's called buoyancy lab, where the so-called ISS replica is in these underwater tanks. And people seem weightless underwater because of buoyancy. Because the density of the human body is close to the density of the surrounding water. If you put some weights onto your body, then of course you're going down through the water. Or if you create a force artificially with your arms and your legs and you're diving down, then of course you can also go down through the water. But in general, if you don't do anything, you can just float in water weightlessly, and that's buoyancy. If you put a weight onto yourself and you're going down, that's gravity. Or if you put air into your lungs, you fill your body up with air and you're rising up through the water, that's gravity. Okay. So a slight difference between buoyancy and gravity. But both is being influenced by densities. And this whole equilibrium or equalizing, because it's a constant thing that is happening, although it seems sometimes static, but it's like constantly happening, this equalizing or balancing of densities. And one thing about why walking on the surface of Earth as people is not proof that Earth itself is attracting us. It's very simple. Imagine a shipwreck at the bottom of the sea, and you're throwing a stone into that sea, and then now the stone is moving down, is decreasing in altitude, is falling through that medium of water until it hits that shipwreck. Now, people who are like that stone might come to the theory or the conclusion that there must be some sort of force coming out of that shipwreck that has attracted me. You see, when that shipwreck is just a surface, it's just a flat plane, and you landed on that because you can't go further because it's blocking your way all the way down to the bottom. And then again, the bottom of the ocean or of that sea is just a surface you're landing on because of densities, because the bottom is very dense, your body is very dense, they hit on each other, you cannot go through that. You see, and that explains why there is a clear down and up in our universe. But then you have the ball theory people that claim that people in Australia walk upside down, being stuck to that ball. And they could never find any proof for this. There are no pictures, there is nothing. You cannot do this because it doesn't exist. There is a clear up and down. Okay? People don't walk upside down. But they want you to believe that everything's upside down, such as people can float in space. In some magic can that is howling through space, which is called the ISS, people apparently are weightlessly floating, when actual physics tells you that a human body always falls through gas. It's weightless in water. Human body is weightless in water because itself consists of 60% of water. And there you have buoyancy. And that creates this illusion of weightlessness, which is the next point, which ties to gravity, because that would be sort of zero gravity because there is no movement, no direction happening. It's then buoyancy. So you're in zero gravity when your body is in water, but not when your body is in gas. You can go 1 meter up into the altitude of gas, you can go 1,000 meters, you can go 10,000 meters. You will always fall through that gas, through that giant medium, because of densities. And then that's gravity as well, because it has a direction, you're falling down. That's gravity. Once you fall into the water, you might fall for a few seconds, go a little bit further, and then buoyancy kicks in. And then that would be zero gravity. And it would be buoyancy, you see? Because then everything is being balanced out. There is no movement going on. So there's a difference again between gravity and buoyancy. Gravity describes a movement, a result of all of the forces that come together, and buoyancy is just that static kind of, it seems to be weightless in that moment. An object seems to be weightless. And that's something also that's behind gravity, is mass, or the distinction between mass and weight, because mass is always the same of an object. If you don't add mass to it, we're saying, okay, that mass is constant of a human body that is falling through gas and then going into water. The mass is always constant, but the weight changes, because the weight is what you're measuring in a certain moment, in a certain scenario, depending on the surrounding medium. So the surrounding medium might be a layer of air, then the weight that we measure is huge, because what we're measuring is the result of all of these forces, and that has a direction pointing downwards. Then the human body in water, because itself consists of 60% of water, floats weightlessly, almost weightlessly in water. and you don't measure any weight. Okay? And another thing is that weights can also be measured into the opposite direction, not just downwards. You can, for example, measure the weight of a helium balloon when it is pushing upwards, thanks to gravity. Then you put a scale above that helium balloon and you will measure a weight with which it pushes upwards. Also called updrift. And that's about it. So it just depends on where you put the scales and how objects are being distributed because of densities and this whole equalization that is going on. And then you can measure the weight. So weight alone isn't just measured or doesn't refer to some sort of earth attraction, doesn't refer to only downwards. Okay? But still there is a clear down and a clear up. And so when people claim that they are walking upside down on a ball, stuck to a ball in Australia, then they are basically defying the actual physics. Their claim is that that's possible, so they have to come up with that proof actually, but there was never any proof. So assuming a flat surface is the first thing people should do, not assuming a ball earth. They should assume a flat earth first and then figure out, is the ball earth actually true? What are the proofs for that? Because again, as we perceive, reality is that we're standing on a firm, stable surface and everything else is moving. The clouds are moving, airplanes are moving, the sun, the moon are moving, the stars are moving. So why turn it around? Why say, okay, the inversion of that is true? Stick with what you're actually perceiving first, observe in reality, and then go from that. And if anybody claims that it is inverted, must deliver a proof, but there has never been any proof of that. There has never been any proof of Earth's rotation. That pendulum, Foucault's pendulum, is a joke. You cannot prove a rotation with such a construction, with such a pendulum. Also, compass needles always point north anywhere you go on that flat surface. However, on a ball, in a microscopic version of that model of ball, and you have some sort of magnet at north, in the North Pole, or even in the axis of Earth, in a microscopic version that you've built, and you try to hold compasses onto that ball, for example, where Australia is, where people are supposed to walk upside down, then you see that the compass needle is confused. It doesn't know where to point at. You see, because actually it wants to directly point to that magnetic source that attracts the needle, but it can't because, of course, a compass is flat. You see what I'm saying? So the needle cannot point downwards, it can only point into one direction. So that works perfectly with a flat earth, but it doesn't work with a ball earth. So how can compasses actually work in practical reality if the earth is a ball? It's funny how this works, right? And then again, you come back to practical reality and something that is scientifically and practically correct. That's what we're looking for, because something that is just scientifically correct can be a theory that lasts maybe temporarily for a few years, for 100 years, for 200 years, but it's still not true. Within the theory, people came up with a bunch of things, and it made all sense, but the theory is wrong. Okay? Turns out the theory is wrong. So within a lie, it can all make sense, but still, it's a lie. So we have to come back to a practical reality of things. And in the practical reality, there is no airline direct flight route from South Africa to Australia that goes over a supposed South Pole. Because it would be convenient on a ball, if you take a globe, if you take that model, it would be very convenient to actually go from South Africa to Australia. Directly. Just cross the South Pole. You can even slightly curve the pole if you say, oh, it's about the cold. Airplanes don't actually have a huge problem with cold because they create their own heat, the engines, so they don't have that big problem. But anyway, let's say you're curving around, slightly around South Pole, it's still shorter than what we have in practical reality, because in practical reality, the airline goes from South Africa to Dubai to Arabia, so crosses the equator once, goes to Dubai, then from Dubai goes to New Zealand or Australia, crosses the equator again, and that's much, much longer. And you know how greedy airlines are. They don't even give you a refund. So if it's about costs, then take practical reality and fly across South Pole if it works, if it actually existed. But it doesn't exist. And on a flat earth map you can easily see why they actually stop in Dubai or stop in Hong Kong, because it's on the way. And they have to stop because of fuel, lack of fuel. So I guess they don't make it. You have to take a stop there because the distance between South Africa and Australia or New Zealand is actually huge if you lay it out on a flat surface. And it makes perfectly sense why they would go that way, because it's straight. It's in a straight line. But it doesn't make sense if you take the ball again, if you assume the Earth is a ball. Because the closest, the shortest distance between South Africa and Australia is going over the South Pole. Again, let it slightly curve, let the airline slightly curve around Antarctica. It will still be shorter than what we have in reality, than the airlines that we can actually book via the internet. Okay, so come back to practical reality, and then you're starting from there, building a theory from there. But what we have in this world is like upside down again, because we're being bombarded with information, with theories through mandatory school, and people are actually being taken away from practical reality, being stuck to a seat in front of a paid teacher, certified teacher, in a stinking room, and they are completely being disconnected from actual reality. So that's about it.